Okay, thank you very much for coming, for choosing this seminar over, I don't know, some beach vacation somewhere. I'm sure you made the right choice, because today our guest speaker is Professor Nicolas. He is my old friend, and we have known each other for years. You spent some time at DLR. Currently, he is at the University of Aachen in Germany, and he's soon to be head of computational center at the University of Kaiserslautern, also in Germany. And he spent recently a few months, more than 6 months, as visiting professor at MIT, and we are very happy to have him here. We have a lot of joint interest, and specifically in the area of adjoint-based computations. Nika spent a lot of time developing adjoint methods and applications for many areas, and I guess today the specific topic is the application of adjoint-based methods for optimal active flow control. And thank you for coming, and please take over. I should remind you that this is an informal seminar, so please ask questions as you have them. Don't wait till the end of the talk. Thank you.
Okay, Boris, so first of all, thanks for your kind introduction and the opportunity to talk here, giving me this opportunity. Thanks a lot.
Our pleasure.
Okay, so efficient techniques for optimal active flow control, and it's really a presentation about ongoing work. So the first part is about the main ingredient, development of adjoints which can tackle unsteady flows, and in the second part I then come to more algorithmic work, how to extend one-shot methodology. I will explain what it is on steady PDEs, where we have since years work and experiences, and then I will comment on how to extend this for unsteady problems, and I show you also first control problems for unsteady flow control. So optimal active flow control, so I think here I don't need to motivate that. We, for example, want to convince the flow here alongside this flap to reattach by actuating the flow alongside maybe some actuation slit here, located here by pulsed actuation, suction and blowing. And we view this as an optimization problem, so we define these actuation parameters and then search for the optimal actuation. And this motivates gradient-based, sensitivity-based methodologies in this context. And yeah, this is how we set up this as an optimization problem. Okay, you may maximize lift. I formulate it here as a minimization problem, so that's the common way in the optimization community. But you could also have a minus sign in front of the lift, then you maximize the lift. So phi is here the actuation parameter, and W the state variable, which has to fulfill the state PE R equals 0. This here shall just denote the optimization methodology. I wrote down here the easiest thinkable, steepest descent, but you will see we do much more fancy SQP-based methodologies at the end. The key problem is when you have a high number of actuation parameters. You will see in my example it's 170,000, so you have to take care to calculate the gradient, which is a challenging task. And here you have several methods available, finite difference-based, if you do this in real or complex step, doesn't matter, or adjoint-based approaches. So the choice here is for sure adjoint-based approaches, because then you are independent with respect to numerical effort. And yeah, the question now is just continuous or discrete, and what is that? I will comment that in a minute. First message is use adjoints because of independence of numerical effort with respect to number of design variables. So this is what you quite often see. I don't like it. I will comment on it why I don't like it. But your minimization problem with the PDE to be fulfilled as a state constraint you can formalize with a Lagrangian functional. Okay, you have here a transpose. This could be also something continuous in L2. Then you would have the multiplier times R integrated over a flow domain, for example. So that isn't discrete, that could be also continuous in L2. And then it depends if you first derive the optimality conditions and then do the discretization. And when you differentiate the Lagrangian with respect to the state variable, then you get this adjoint equation. So if you derive the optimality condition first and then use the discretization, this is the so-called continuous adjoint. If you do the other way around, you set up everything here on the top already on the discrete level, you discretize your flow problem and have a discrete version of your optimization cost functional, your Lagrangian is discrete, and then you set up the optimality condition. That's the other way around, that's then the so-called discrete adjoint approach. So the necessary first order optimality conditions for optimality are stated here. If we differentiate with respect to the Lagrangian multiplier lambda, this is just our state constraint. Our PDE has to be fulfilled here. Our PDE constraint. The differentiation with respect to the state variable is the adjoint, and with respect to the parameter, this is then the design equation. And please note the partial differential of L with respect to phi is the total derivative of the cost functional J with respect to phi. And the trick of the adjoint is just to solve the flow once, then the adjoint, and then you use this information here to evaluate the total derivative of J with respect to phi. And you just need to evaluate here these partials. So the expensive part, total derivative of J and R with respect to phi is needed. Okay. I said I don't like this. Why? Because it's a little bit cheating. So the continuous problem usually lives in another space than L2, and that is very important. So if someone says he wants to do the continuous adjoint, he should do this in the proper space setting, and that's the first problem. The first problem is you may not know what is this space setting. And then here is an H for the primal space in which W is living. This denotes Hilbert, so you have a Hilbert space. And then you need a primal dual pairing to set up a Lagrangian. And only if this Lagrangian exists, so if I have a Hilbert space setting, I can do this formalism. And the first question is, how looks like H? For 3D Navier-Stokes, we don't know this. If we would know about this, we would get a Fields medal if we would be younger than 40. So for me, it's too late already. So that's the hard truth here. And the other thing, I also don't like this setting for the discrete, because that's not what we are doing. If we are honest, when we solve R equals 0, we have an iterative process denoted here by this fixed point equation. So I have a fixed point iterator G, and I iterate G of W several times until I converge here to the fixed point W equals G of W. So I have, for example, in steady state a pseudo-time stepping scheme, or I have an implicit solve, some backward Euler combined with Newton, whatever. Yeah? And this is the discretization, the algorithmic realization of the solve of the PDE R equals 0. So if I want to do a discrete adjoint approach, I should incorporate that in the Lagrangian. And that really makes a big difference. Yeah? So G minus W, if this is 0, this means R equals 0 holds. I just plunge it in here. And if I then state the optimality conditions for that discrete realization, for this Lagrangian driver program then, in the discrete way, this is what I call black box differentiation. Why black box? Because I differentiate the entire nonlinear solver, not only the flux routine. Okay. Then I end up with this KKT condition. And the nice thing is here, G minus W, this is then converged to a fixed point W. This is here the adjoint. And I have here lambda times identity, so I can put this lambda on the right-hand side, and what remains here, so this part here, this is then what I will note by NWT. That's the derivative of the so-called shifted Lagrangian. I comment on that later with respect to W. But this is this guy here. And the important thing is, I have then a fixed point equation in lambda, and the good thing is I get the convergence properties of the primal solve for free inherited here by the adjoint iterator. Why? I'm iterating in lambda, so if I build the derivative of NW with respect to lambda, yeah, this is then just dg with respect to dw. And if I assume that this converges, so by Banach's fixed point theorem, dg with respect to dw should be bounded by a constant rho strictly less than 1, necessary sufficient for convergence. And this is exactly the condition also for the adjoint iterator, for free. Yeah? So that makes really the big difference. So if you linearize instead here in the R, and you solve this system of equation, I can tell you, and most know that, this guy here is very having very high condition numbers. So this problem here is ill-conditioned. You inherit then convergence problems and accuracy problems. And here you have the nice thing, if the primal converges, the adjoint converges with the same contraction rate rho. Okay, and that means now we set up this Lagrangian driver program and differentiate in a black box manner with respect to G minus W, this whole guy L. And this you can set up with the help of automatic differentiation. So I will not go too much into detail here. What is automatic differentiation? This is, for example, when you do it operator overloading based, that's easier to explain. So you have the input of your code, and then you have the output of your code, and you can differentiate the output with respect to the input. How? Yeah, when you send your computer program, which reads in the input and delivers the output to the compiler, then it is during compilation translated to elementary operations. And if I differentiate them all and then concatenate everything by chain rule, I have the total derivative of the output with respect to the input. And if I do this in reverse order, this is then the pendant of a discrete adjoint. Yeah? But what we do is we differentiate this Lagrangian program with respect to the same variables. Now the question is, we discussed continuous adjoints and discrete adjoints. What shall we do? How do they compare? What is about consistency and commutativity? The answer is usually you don't get commutativity. That's bad news. Quite often the continuous adjoint problem doesn't exist. If you do a serious analysis, you don't know space setting. Even if you know it, quite often then, when you go to the numerical realization, especially when you incorporate turbulence models, you have the problem that then you have mathematically non-differentiable things involved. So then the question of commutativity, of discretize and optimize, or optimize and discretize, is doubtable, questionable. Here an example, incompressible Reynolds average Navier-Stokes plus turbulence modeling. Here it's K omega SST. So here for eddy viscosity mu t, we have to solve the additional coupled system for K and omega. And we know when we go to the boundary, to the wall, that omega tends to infinity. So this turbulence model is not differentiable. So that means if we would like to do a continuous adjoint, derive optimality conditions first, we would assume mu t to be frozen. Yeah? Then the derivative is 0. Otherwise, we get problems. Yeah? It doesn't exist. Yeah? So And this frozen turbulence assumption really leads to extra inconsistencies. I have done both over years. I can tell you the effect of freezing turbulence is really ugly. You shouldn't do that.
But now often people, for SST, they don't use infinity at the wall. They have that approximate boundary condition, which is infinity.
That's a good argument, but mathematically speaking, you are completely right. This is why I suggest here to apply, for example, automatic differentiation. Then it works. You're so right. So the omega is modeled by, say, 1 divided by wall distance squared, something like that. And this is, of course, algorithmically differentiable. But mathematically, the continuous would say wall distance goes to 0. And then you have your infinity back, okay? And that's the problem. So in practice, you are so right. And that's the reason why I say do it the discrete way here. That works. Algorithmically, you can differentiate this 1 divided by wall distance squared. Okay, thanks for the question. Okay, so this is the solver involved here. I forget to mention all the collaborators at the beginning. This is joint work with Frank Thiele's group in Berlin, Felix Kramer and Tobias Höll. And from my group, it's Anil and Emde. And in Collaborative Research Center in Berlin, we were applying this code on heavy flow control problems. So it's a standard Grant's solver here, block structured finite volume method, incompressible, and the velocity pressure coupling is done by simple coupling loops. It's fully implicit, MPI-based parallelization, and there's a bunch of turbulence models in. We concentrate on the SSTK omega. So Frank is a well-known expert in turbulence modeling. There's much more in. It's coded in Fortran. The AD tool we applied here, that's the setup of the adjoint solver has been done in my group by Tabelnade from INRIA. Here we have good collaboration with Laurent Asquet. So this is source to source here. We can discuss later. It's another detail. And you cannot, I said we do black box differentiation, that's true, but not in a stupid black box manner. Yeah? So we use a lot of extra features like reverse accumulation. For example, for the simple coupling loop, for the coupling pressure velocity, we don't tape all the intermediate primal couplings for the reverse run. There we read in the finally coupled. That's the so-called reverse accumulation. You can prove that this asymptotically converges to the same as if you would have done carefully the taping of the intermediate primal solves. Okay? For example, that. And then we apply checkpointing. We apply mainly static checkpointing, but you can do this also dynamic. Then you save a little bit. That is, by the way, work of Chi-Chi Wang, my collaborator at MIT. The last part of the talk you will see Chi-Chi is involved heavily. He has extended the revolve to dynamical checkpointing. So what is this checkpointing?
Nicolas, let me ask you this question. When you're solving the primal problem, you have to drive down the residual.
Yes.
Assuming we're seeking some steady state solution. Now the point is that when we say drive down the residual, what precisely does that mean? Does that mean 6 orders, 4 orders? What does it mean?
Charlie, a very good question. So, in fact, we are completely independent by that. We have this iterator G, and the level of convergence in our approach is not important. If it is 10 to the minus 4, 10 to the minus 6, whatever, we are fine. Yeah. If it is not converged close to, say, machine accuracy or something like that, we are not in a fixed point. We don't apply reverse accumulation for the outer loop. Yeah? Then we view the derivative as the derivative in, say, capital N many iterations G. Yeah? So that would mean that even when we have a steady state solve, we would then take care to differentiate alongside this n times applied operator G. And then we get the exact derivative of this mapping G to the power n. applied on W, whatever that is then at the end. But for this level of accuracy, we get then machine accurate derivatives. Yeah? So if you as a guy who is doing the simulation promise me 10 to the minus 4 is okay, then I trust you and do the perfect exact optimization on that.
In the first place.
But that's a very good point, because this other way around with the discrete approach, linearization in R, this is the pendant to my approach, applying reverse accumulation, reading in, so to say, W star always when I'm in the reverse sweep. And then this converges asymptotically only if I have really a good approximation of my, say, Wn close to W star. Yeah? And that is something you cannot promise in practice. Yeah? Quite often you have some areas with poor mesh quality and things like that. So thanks a lot for this very important question. That's a key thing in the application. Oh, checkpointing, I should explain. So checkpointing is a combination of two strange brute force methodologies, the store all and the recompute all. So the store all is you really store alongside your physical time steps or your iterates G, however you view it. You store everywhere, and when you are then in the adjoint reverse trajectory, you can always read in the appropriate primal state needed, or previously states needed. Of course, this is excessive memory requirement. Recompute all is excessive with respect to computational time, but you store nothing. Yeah? So this means you forgot everything alongside the primal trajectory, and for the first reverse sweep, you need this guy, you recompute all and forget, and so on. Yeah. So here, no memory, high computational effort here, high memory effort, low recomputational effort. And the checkpointing, therefore, I show these two extremes, is just an intelligent combination of these two extremes. You distribute so-called checkpoint sample points where you store your solution, and at the end, you store what you can afford to store or what you are willing to store. And between this last section, as explained, you distribute binomially distributed checkpoints. Why binomially distributed? It's a combinatorial problem. It turns out if you distribute them binomially, the recomputation, which I explain soon, is then minimal. Yeah? How does it work? So at the beginning you have everything available, and here's the first point missing, then you go to the next checkpoint, do a recomputation. And this you store here. You can overwrite here, you don't need these guys anymore. And for the next, again, yeah? So it turns out for one extra computation you can gain 90% in computational effort. This is for this code, and I show you now a heavy application of this code. It has a runtime ratio of the adjoint provided by automatic differentiation compared to the primal of 6.7. When I store for 100 physical time steps, all the 100 is 6.7. If I just store 10%, then it's 7.8. Yeah? This is the increase in runtime ratio by increased gain in memory, so less checkpoints. So my thumb rule is store something between 10 and 15%. Then you gain 90% in memory. Now we come to the application. It's kind of crazy, but it dates back to a history. So there was this collaborative research center in Berlin, and I had some time in Berlin some years ago. That is where I met then Frank Thiele, and we came together. So they had a half wind tunnel model, as you see here. It's an Airbus configuration, the so-called Hyrex configuration. Top view, bottom view here. And here on the shoulder, the nose of the shoulder of the flap, alongside here you have an actuation slit for pulsed actuation for suction and blowing. And for this, we have a wind tunnel model and can do experiments. We have set up an adjoint here, and then we said, hey, now we are rich. Yeah, we are rich men. We do a rich man's approach. So that means we can afford as many as design variables as we want, and we spread for the numerics a lot of actuation on the top side and the bottom side, and alongside the fairings. This will be very important, as you will see in a minute. And yes, then we detect which areas are really sensitive with respect to actuation. Yeah? There we did a first optimization. I show you the results. And at the moment, on our supercomputer in Aachen-Jülich, we have a running optimization for the dominant areas for a much bigger time window. Here you see unactuated flow simulation and actuated flow simulation. This is it's a 48 million cells mesh, 1.5 million is Reynolds number, angle of attack is 7 degrees. We use this code from Frank and our adjoint capability as explained, and you see here a validation. Lift polar meets nicely the experiment, and this is now how the lift involves for the actuation on this first slit on the shoulder of the flap when the actuation intensity increases, and you see we are in a margin of 1% accurate.
What's the nature of the actuation? Is it oscillatory or just steady blowing? Or?
No, it's pulsed actuation.
Okay.
I show the details of the modeling.
So this is all time dependent?
It's all time dependent.
Okay.
Yes. Good point. I come in detail on that. So this is how our code performs on the Jülich computer. It's quite a monster if you would have it completely available. I think it's ranked 3 on the top 500 list. We have a big fraction of these 500,000 nodes. We have 16,000 nodes available, a gigabyte run per core. That's a big performance if you would have the complete machine. And we measured the performance on a slightly smaller mesh here, which is having cells nicely dividable by 2. And you see how nice the primal code and the adjoint code performs. The adjoint seems to perform better. That's clear. You have more operations per node. And at the end, you get here also down in the...
But your code is based on the block decomposition. Are you constrained by the block topology?
No, it is. Yeah. Oh, yes. It's a structured solver, if you mean that. It's a structured multi-block solver, yes. Okay, so, and this is for the optimization we are running right now, the numbers. So on this we have a primal solve 34 hours. An adjoint one is not a factor 7, but a factor 8 because of the checkpointing, as I explained to you. That's one extra computation. So it's a factor 8. So for one very rough, simple optimization with 5 optimization cycles, we need 85 days. That's running at the moment for the detected important areas. I show you the pre-study now. We have 33,000 cell faces alongside these slits, as I have shown you, and we have 5 variables in each phase. So in total it's 167,000. And now I come to your question, Eric. So this is how it is modeled. We have a velocity vector modeled here, periodic, so it's pulsed. And we have an angle alongside and perpendicular to the slit. This is beta 1 and beta 2. And we allow to change the frequency of the pulse actuation, and we allow a phase shift in this pulse actuation.
Geometry is fixed.
Geometry is fixed.
There is no...
No, it's not a morphing thing. It's a regular Airbus type high Rex configuration with this kind of pulse suction and blow. This is the initial actuated flow. And here you see the sensitivity validation. The dominant part is the phase shift. Order of magnitude is 10 to the minus 5 here. And you see here up to 16 digits correct. Yeah? So this dominates. The other are of lower order, so this is more than machine accurate. Yeah? That's really perfect. Yeah? Cost functional here is mean lift. And now you see over a time window of roughly 1,200 physical time steps how the adjoint sensitivities perform in our steepest descent methodology. And I would say here in this last section here, where we have the optimization.
Just to make sure,
yes.
find the difference on previous slide was
Yeah.
complex variables, right? So it's when you compare, find the difference in adjoint.
No, because I compare here the discrete that wasn't complex.
So how do
Okay.
you know, okay, how do you know the discrete find the differences, right?
You're right. I could say you are somehow right. It was kind of complex step because we compare with the forward mode of automatic differentiation, which is equivalent to complex stamping. Okay, so we really can calculate the finite differences with step size 0, so to say.
You know that finite difference is right, so it's
Yes.
how you compare adjoint, and that's
Exactly.
verification.
Yes.
Okay.
So we first, that's how we set up the adjoint always. We first differentiate the code in forward mode, which is already a pain in the ass, sorry, but it's true. And then we are sure that this fits to common finite differences. And then we set up the adjoint solver, and that has to be machine accurate in comparison to the forward mode.
Remember
And
that
that
you
was
are online, and so whatever you say remains forever.
okay, but it will be forever a pain in the ass. So even if this is online, I have no problems with that. It's just the truth, okay? So, but you see here, we have. Thanks, Boris, for this late information about this camera. Yeah? Okay, so we have an improvement of 125 lift counts. But now we come to the interesting details. These are the sensitivities. Here now for the amplitude, and if we zoom in, so this is alongside the shoulder, so that's impressive. This is this first slit, so the engineers really did know what to do. That was the slit they defined in this project in Berlin. But here red is high intensity of sensitivities. We have not only in this area high sensitivities, we have it also here alongside the pharynx and close to the pharynx. So we have a mechanism also from the top shoulder, then the pharynx, from the main wing to the flap, and on the lower part of the flap. So Airbus is very attracted and interested in that for further investigation. And that makes the difference. Yes?
Very, very simple question. Is it blowing perpendicular to the surface of the fairing, or is it blowing tangentially?
This angle beta 1, beta 2 is really varying. You have locally very different patterns.
Okay.
Yeah?
Thank you.
This isn't published. We have some discussions about patent matters and things like that.
Understood.
Okay, here's for the face. It's always the same. You see here always on the pharynx also this red area. Angle 1, angle 2. This is the top view of the initial and optimal actuated, and the bottom view here you have again the strong areas. Here on the main wing part, interestingly, connected to the fairing and alongside the fairing. Okay, so this is the summary so far. Before I come to a further, more algorithmic part, more mathematical part, a discrete adjoint method for incompressible rands based on AD has been developed. The key ingredient was AD has been applied to the Lagrangian driver, including the entire nonlinear primal solve. Thus, we inherited convergence properties of the primal solver, and the primal and the adjoint are both very robust and accurate. And we could improve the mean lift by these 125 counts. Eric, you had a question?
So I want to go back and reconcile some of the earlier on when you were looking at checkpointing or not, and kind of asymptotically what the adjoint runtime was going to be if you had all the data in core.
Yes.
And I think the conclusion there was a factor of 6, 6.5, or something like that.
6.5 is really, that has to do with checkpointing. 6.5 is really the factor adjoint compared to primal. But this is mesh level independent. That's the good news.
Right. So now on this big problem, can you flip back to the chart where you were showing the runtimes for this problem?
Okay.
You were paying a factor of 8 for the adjoint. So
Yes. That is 6.7 is for the adjoint, and 1 is for the recomputation with respect to checkpointing scheme.
So I haven't worked through
Yeah.
in my head how much data that is, but
It's
would
a
you
lot.
say off the top of your head, though, that you do not have a disk space to take the brute force, store everything approach? I'm not advocating that, but that's where we are, and I haven't hit the wall yet on that approach.
Yes.
We have disks that'll store many, many terabytes.
You're right. That's something I will concentrate on my new job in Kaiserslautern.
Because right now,
Yes.
if I go to Mehdi and tell him he's got to spend 8 times an analysis,
Yes.
it's going to be game over.
Yeah, you're right. But the good news is, okay, it's a factor 8, but you are mesh level independent. You could go with this methodology on much coarser meshes. It's still robustly convergent. So on a structured mesh, you have from one mesh level to another global refinement already in factor 8. Yeah. So the truth is really it's not so less efficient than other methodologies. And we could even afford and store all approach if we would have per each core, we are having 16,000 cores here involved, if we would have a huge amount of memory locally available. Otherwise, the I/O costs us again a lot of time. It's not only a memory F.
Well, I guess our experience has been we've been successful so far in mitigating that overhead.
Yes.
With a parallel file system out to a decent number of cores.
Yes.
I don't think that's going to work forever. I think checkpointing is the way to go.
Yes. Yes.
So you're saying if store all, then it's just 1-to-1, it's 34 hours, 34 hours.
Our adjoint solver costs less than our full
Oh,
solver.
even less.
Yes.
Yeah.
If you do it head discrete or continuous, then you have usually the adjoint less costly than the primal. But we could discuss about robustness.
There's a lot of pros and cons. We put a lot of time into our I/O, for
Yeah.
example, how to do that.
Okay.
And the differentiated work.
So this is now ongoing work here. We repeat this for a bigger time window, not 1,200, but 20,000 for the dominant areas where really suction and blowing pays off. So shoulder of the flap, then the pharynx and designated areas of the main wing and the flap on the lower part close to the pharynx. Now the question is, because this is so costly, and then that's another pro of our approach. Our approach is so correct and consistent and robust that we can incorporate it into one-shot methodologies. And what's that? So the question is, could one-shot methods do this job to do this very efficiently? So there is a big roadmap behind the work we are doing here. So we are here in the outline of the talk. I must speed up, hurry up now. I recapitulate one-shot methods now for steady PDEs. So the idea is just to break open the inner nested loop, like Shlomo Tazan already suggested in '92, and to converge everything all at once in one shot. So do one update in the primal, one in the adjoint, and immediately a design update. I'm doing this since long time with two main collaborators for the continuous adjoint based with Volker Schulz in Trier and with my good friend and old mentor Andreas Griewank in Berlin, the discrete way. What I'm showing now is on the discrete way. So that's the problem set up for steady PDEs. We are minimizing a function. It's now denoted by F. Y is the state variable, U the control, C is the PDE. So And we solve the PDE again with such a fixed point iterator G. So we iterate as long as we converge to the fixed point y star. Contractivity is the assumption for convergence by Banner's fixed point theory. We set up the Lagrangian driver as explained, and then we set up the KKT system. And compared to the nested approach, the one-shot is different. So the nested says, I converge fully the y star, the state, then I set up my adjoint iterator, I converge fully with the read in y star until my adjoint variable y bar star, and then I use these two informations to evaluate the design update with maybe some preconditioning in front. The one-shot approach is different. You do just one iterate in the primal, one iterate in the adjoint, and then an iterate directly in the update. And the question is how to choose this preconditioner B, which you definitely need to ensure convergence of this all-at-once approach. Here the discrete, since 2008, joint work with Andreas Kliwank and the former postdoc of Andreas Adelham.
Is the extension for time dependent?
I show you
Okay.
the extension for time dependent. And that makes it extraordinarily interesting and heavy.
Right, because-
Hardcore, as you will see. But it does.
I-
Okay. But I must explain you the theory, and it's easier to explain it for the steady PDE. Okay. So we do this. So this is the shifted Lagrangian, as I had before already. This guy. This is here then the shift to the Lagrangian. Then I see immediately this iterator, and we know we can simultaneously iterate the adjoint with the primal by the so-called piggybacking from Andreas Kliwank. That has been proven in a paper from Andreas and Christel 4 in 2002. And that's very good news with respect to memory. You solve this all at once. So when you have your primal step, you do immediately your adjoint. Yeah? And that converges with the same numerical effort. But if you now incorporate here, also the design update, you can expect one-shot convergence without choice of improper preconditioner B. How to do that? So the first you have in mind is you analyze the Jacobian of the optimality system here and the limit point k to infinity. So these are y bar, and u, k plus 1 variable differentiated with respect to k. In the limit point evaluated, we have this Jacobian. And if this would be less than 1, you would have convergence 2 as a necessary condition. And the idea is we want to choose the preconditioner B such that we have so-called bounded retardation. So this means the retardation of the convergence process of the all-at-once coupled one-shot scheme, yeah, compared to just a simulation shall be bounded. That is what we call bounded retardation. So how to ensure that? Then we have a small effort of an optimization compared to the simulation, and I will show you shape optimization examples for 3D cases. It's a factor 2. But that only works for consistent discrete adjoints because you start to converge everything from the beginning on. If this isn't consistent, this information is not physical, it's just mathematics in crazy discrete mathematical spaces, then you have no chance. Yeah? Let's play now tennis back to you, okay? Eric? Okay. It turned out that deriving at least sufficient conditions for this preconditioner B, such that this coupled Jacobian has a spectral radius less than 1, has proved difficult. It's natural, the Lagrangian has to do with the design problem, because we do have an increment vector in primal variable, in adjoint, and in the design, to add to add two further terms. And we decided for primal and adjoint residual, weighted by alpha and beta. And I will show you, or we have seen this in theory, we have written papers about it. By the way, that works for all optimization problems with PDE constraints where the PDE is solved by a strictly contractive fixed point scheme, yeah? Independent of aerodynamic applications. It's a heavy tool. Yeah? We have also applied it in meteorology already. My colleague in Kiel, Thomas Slavik, for example. Okay, it turns out that this is an exact penalty function for our initial optimization problem, and the gradient of the augmented Lagrangian can be expressed by this matrix times this increment vector. So this is the increment in the primal, the adjoint, and in the design. And now I have a one-to-one correspondence between stationary points, so fulfilling a necessary condition of KKT with respect to the augmented Lagrangian, which is an exact penalty function with respect to the Lagrangian here on that side. It's a one-to-one correspondence to the zeros of the increment vector if and only if this matrix M here is non-singular. And furthermore, if this matrix N, because I have a minus sign here in front, is positive definite, I assure descent in each step. And that's exactly what we are doing. So I'm assuring that the determinant of this guy is different from 0. I develop the determinant alongside that line, so B shall be positive definite and symmetric anyway, as in preconditional and design scheme. So this subdeterminant here shall be less than 1. That's the necessary condition for this one-to-one correspondence between the zeros here and the stationary points there. And furthermore, if I strengthen this condition as I show you on the next slide, I have positive definiteness of M, and I have further to show an angle condition and things like that. Yeah, there are some papers. Just to give an idea, if this inequality for alpha and beta is fulfilled, we have this convergence for sufficiently large B's. What means sufficiently large? This means this guy. Now you say, gosh, where the hell is this coming from? But it's quite easy. If you look the Hessian of the augmented Lagrangian, the reduced Hessian with respect to U, this appears here plus extra terms, and these extra terms are weighted by the residuals in the primal and the dual solve, which tends to 0 during the scheme. So in practice, this is what I'm doing together with Emre, we evaluate the reduced gradient of the augmented Lagrangian by automatic differentiation in our schemes presented in the first part of the talk. Then I do a BFGS update of this Hessian, and therefore an update of this B, which does the job. Now you may ask how to evaluate this guy. This you don't do, but that is nothing than a Lipschitz constant of the adjoint iterator with respect to perturbations in the initial primal state. That's something you just measure, yeah? But a good hint, choose it one, it works. Yeah? And choose beta and alpha. That way, you see rho is quite close to 1, so alpha is much bigger than beta. That does the job. And this is how it performs. Here we reduce a shock on a wing. It's transonic Honora M6. Retardation factor with respect to iterations is 2, but because we have this overhead in computations of preconditioners and so on, it's a factor 5 in wall clock time. But it's mesh independent. No wonder it's close to a Newton's method. You see here all, and this is unstructured solver here. We did it for the tau code 2. You see here DLR tau code. You see here 18,000 surface mesh points for the coarse mesh, and then globally refinement. Of course, you have a difference here due to spurious drag. This is implicit here, but it's mesh independent. And that motivates to incorporate even adaptivity here. This is global adaptivity here. We converge first on a coarse mesh, and then we continue on a fine mesh. Then we can halven more or less computational time. A further PhD student of mine has incorporated dual-weighted residual methodologies. It's Lena Karlan's work that also works nicely because you have the DVR sensor for local mesh adaptation in hand because you have the adjoint incorporated in your one-shot loop. And this is a complex application of this guy, the DLR, very efficient large aircraft, the big body configuration.
You use only global refinement, so you basically use solve on coarse grid and
here it's local refinement.
Oh, so
that's
local refinement.
Yes.
Okay.
That's local refinement. And here you see for really a factor 2 also, and this factor 5, this we have published already 2011 in AIAA journal. We really can dramatically reduce the shock while lift is fixed. And now the question is, can we do this, Boris, your question, also for unsteady PDEs? So what are the adjustments here? We have now a time-dependent term added, and we illustrate the scheme here to something which is close to what is in this ELAN solver we have had in the first part for the Hyrex optimal flow control. So a simple, thinkable, implicit time margin scheme alongside a really physical time trajectory. Okay? So we have to solve this set of equations alongside the physical time trajectory from T0 to T capital N. This is what we have. Alongside, for each physical time step, we have an iterator G, which makes use of previous time step solutions until convergence. And it shall be contractive in each physical time, otherwise it wouldn't converge, and that is assured by contractivity of these guys here. And now the question, how to incorporate such updates in one shot, in this unsteady case. We modify now the scheme that looks in the first moment a little bit crazy, okay? So what we are doing is, we do a loop reversal. So we do alongside a physical time sweep, only one evaluation of these inner loops G. Yeah? So the inner loop becomes the outer loop becomes the inner loop. So we consider updates in a vector of states, a vector which contains vectors of states, cell-wise, with respect to physical time steps T1 to Tn. So we have some updates G alongside the whole T always. And for this new state in this product space Rm to the power n, we have denoted this to be the function h. Yeah? This is this operator which evaluates one G iterate alongside a physical time trajectory. And if you now do an analysis of h with respect to y, it turns out that the Jacobian h with respect to y has block triangular character, and on the diagonal we have this guy here. We can now estimate the spectral radius of this Jacobian by the maximum of the spectral radius here, which are all bounded by rho less than 1. So it's contractive.
So UG is kind of point iteration,
yeah.
Right? So you should insert iteration basically.
Yes.
So if I use something like more involved implicit solver that maybe use, I don't know, defect correction type of things and precondition.
But that's in fact what we have. I show you an application already, and then we view this as an iterate G. Yeah? Now the question is, can we do one shot with this approach? So first of all, we have h is less than 1. So we have fulfilled everything as before. Yeah? So we have the same structure as in the steady case, and we can apply the one-shot method. Yeah? So we have now capital H replaces G. We have here the same assumption of contractivity that has been proven before, so we just can apply it. The Lagrangian looks as before. Now we have just an H here, and an update K, an iterate in K, means always evaluations alongside a full time sweep forward and reverse for the Y bar. And we have applied it for control on a cylinder. We have just Kalman vortex shedding here. Then we have lift-induced drag, which we control by pulsed suction and blowing, and the amplitude of this pulse suction and blowing is here, the design variable. And the nice thing is it works. The one-shot converges here nicely. This is the cost function. This is the norm of the gradient, primal and adjoint, and this is the initial drag and the mean drag after optimization. It works, but now comes the intermediate bad news. It's bounded retardation still, but dependent of the resolution of the physical time space. So this capital N, I have a linear dependence in the capital N. Question is, can I solve that problem? Can I prove efficiency here? And that is where I got into contact with Chichi, so that I presented, or my PhD student Steffi presented that 2013 at the Science CSE in Boston, and then Chichi said, hey, I have some studies on the Thunderbolt, apply it in that way, or in that framework of one shot, it may help. And the answer is, it doesn't help only, it is the solution, at least for this model problem, as I will show you in a moment. So after spatial discretization, we have an ODE solved problem. So we choose the Thunderbolt as a model problem. I come to a more complex model problem later on, because we have non-autonomous ODEs, and we have something closer to Navier-Stokes we choose in the next step, advection diffusion equation. So here it's an autonomous ODE, and we use this crazy scheme which we apply in the Elan code for one-shot optimization. It's a backward Euler discretization with a quasi-Newton fixed point solver. If we would do Newton here, it would converge in one step. Yeah? We want just to mimic the behavior. And we have this loop reversal, so this modification for one shot. So we have this outer iterates k. And what you see here is the solution, and here you have different colors, and yeah, each color represents an iterate k. Yeah? Blue here, that's the first iterate, and then each change in color is 10 steps, so it needs some time to converge to this green line with these triangles here. What you see is, qualitatively, the solution is from the first step on quite nice, but quantitatively it is not. I have this so-called numerical time dilation. So in the first iterate, the longer I go along the physical time trajectory, the farther I am. I'm having a time shift in the numerical approximation. And the idea is now quite simple. Minimize the residual area by adapting the time step. So minimizing such over the step size ti that the optimal ti tilde minimizes this residual error. And for autonomous systems, you can explicitly solve this. It's a baby problem here. You can solve this explicitly. That's the solution. And if I apply this adaptive time step here for this loop reversal, then I have already, after the first rescaling, the perfect match. And it turns out, here you see the residual behavior with respect to increasing k of the scheme without time scaling and with time scaling. Without, you have to iterate like hell, and the farther you are physically in time, the less the improvement in the residual. Yeah? So it takes a long time. If I would converge it like on the right hand side to 10 to the minus 14, I would take much more iterations. The good thing is with this time rescaling, I have the residual error independent of the length of the physical time domain. So therefore, this is without time rescaling here, the convergence of our scheme, and this is with time rescaling. So with time rescaling, we have independence of the number of time steps alongside the...
So your time step becomes smaller as you progress?
Not necessarily smaller, it's adaptive. That means we have a little bit, some part at the end is missing. It's shrinked together.
Okay, so it's my concern. So
yeah.
Can you get into the situation when you actually do not advance in time, right? So
no.
Time becomes like 1/2 of the
yeah.
previous, and so
it's not the case, but that's just a model problem. Right. It's not worth to discuss this here. You will see other problems on the next slide. Okay, let's postpone that. I'm really sorry, but some slides here are just missing. So results now. The nice thing is here, it's really independent of the number of physical time, and we have one and the same retardation factor 7 still for the unsteady problem. What we are having here is we fit a reference state belonging to a factor mu here in the van der Pol problem, and we do as if we do not know the mu, and we fit now with our optimization the mu such that the state fits the reference state. And of course we do a Tychonoff type regularization with respect to mu here to have a well-posed inverse design, which one usually should do. So this is a retardation factor 7. One-shot works here. But now, more realistic things. You have a lot of other problems. Boris, not only your concern. We have now advection diffusion equation to have something more realistic to our Navier-Stokes. Plus we have here on the x position 0 a periodic time periodic state u coming in. And that means the ODE is first of all no longer autonomous. It's non-autonomous. And we observe not only, here you see in zoom, not only the time dilation, but also an error in the amplitude. But it turns out, if we do a transformation of this system to an autonomous ODE, which is by some very easy trick always possible, the easy trick is the following. We do this transfer, we add to the state vector an S of t, which solves this ODE. So this is, the solution is just S of t is t. But then I would see the dependency here, and so it is independent. Yeah? But the linear problems may become non-linear by that. But nevertheless, I can get it autonomous, and at the end, I can then apply on this new state vector W extended by this parametrization S. I have again this adaptive time scaling. And it turns out, then I have just this time dilation problem, no longer an error in the amplitude, and I have this nice shift here. But I'm not really perfect independent. In my improvement, I have an improvement of 5 orders of magnitude. Yeah, this is without time rescaling, this is with time rescaling. That's already quite nice, but we are far from complete independence. Okay? And these concerns you had, so now I'm really done. The concerns you had, Boris, I would say for the initial step you should have a little bit more physical time iterations, and then when it shrinks due to the adaptation, you should be sure that you still resolve the physical time domain. That's possible by easy tricks. That's combinatorics. But that's ongoing work, and what I'm doing at the moment now, together with Chichi at MIT and my PhD student Steffi Günther, we partition the physical time interval, and we do parallel in time solves, and we are using this technique of shadowing in order to close the gaps between the jumps in the approximations time interval by time interval with an outer Newton solve. This ill-postness with respect to initial data and ending data, it ends up in a boundary value problem where you have to match. This ill-postness, this jumping in the initial data, we overcome by this shadowing, least square shadowing technique. I don't like this expression. I would call it Tychonoff regularization with respect to initial data. And this we want to incorporate into one shot. So, and we hope that this works better than the just time rescaling. But the time rescaling one could use as a sub-powerful tool then on the parallel in time tools. So you have seen we are doing big applications, the best as we can on a university level. We have in mind scientific computing aspect, computer science aspects, and also a lot of mathematics is involved here. And we are more than convinced that you need a lot of good ideas to solve these problems in a reasonable time in the future, and we hope at least we are in a good way. So that's the parforce writing we have done here through the content I have promised you before. So thanks for your attention, and I would be happy to answer further questions and discuss with you guys. And thanks again for the opportunity being here. Okay.
Thank you. Questions? I have a lot of questions.
Yeah. So we can continue in your office also.
Yeah.
And you guys had already a lot of
Yeah, as I
questions in
promised.
between.
Okay, then, so we'll
Thanks a lot.
continue then in my office.
We do that.
Thank you very much.
Thanks.